We are now discussing about complexity classes. In the previous lectures, we discussed about class P and class NP problems, and also we have seen polynomial time reduction. And in this lecture, we are going to define the class NP complete and NP hard by using polynomial time reduction. So I hope you remember what is polynomial time reduction. Otherwise, please watch the previous lecture before you see this video. We shall see these two new complexity classes, NP complete and NP hard. Let us recall class P and class NP problems that we already discussed. What is class P? Those problems for which deterministic polynomial time algorithms exist for finding the solution. Example, sorting is a class P problem because there is an n log n algorithm for finding the solution for the sorting problem. So a problem is said to be in class P if there exists a deterministic polynomial time algorithm to find the solution for that problem. Now, class NP. We discussed about two different notions of NP. Here we will be using the notion where the existence of a deterministic polynomial time verification algorithm defines the class NP. So these are those problems for which deterministic polynomial time verification algorithms exist for checking that a given solution is a correct solution. So these are anyway hard problems. So if someone is giving us a possible solution, then can we verify that the given answer is a solution? If you can verify that using a deterministic polynomial time algorithm, then the problem is said to be in the class NP. This is a notion that we discussed. Example, the non-deterministic algorithm for vertex cover is of exponential complexity. But if someone is giving you a set of vertices claiming that that set forms a vertex cover, then we can use a deterministic algorithm to verify whether the given set is a vertex cover or not in order of n square time. You check for every edge, one of the n vertices is in the given set or not. So that is what you have to do. So it is an order of n square deterministic algorithm because n square edges are there in the maximum case. So this is class P and class NP. Now we can see an application for polynomial time reduction in talking about the complexity class of a problem. Suppose T1 and T2 are two problems. See, they are problems because I am using P for polynomial time reduction. I am using the names of the problems as T1 and T2. And suppose T1 is polynomial time reducible to T2 and T2 is not to be in the class P, then we can prove that T1 is also in the class P. And if we can prove this, then polynomial time reduction is helping us in identifying the class of T1, the complexity class of T1 as P, when T1 is polynomial time reducible to T2 and T2 is not to be in class P. And to prove this, you need to know the definition of polynomial time reduction, which is what we did in the previous lecture. Now look at the proof. So the claim assumes that T1 is polynomial time reducible to T2. Then by the definition of polynomial time reduction, that means there exists a polynomial time reduction function f from T1 to T2. This is what we learned in the previous lecture. Now in the claim we also assume that T2 is in the class P. T2 is in the class P means by definition of class P, there exists a polynomial time deterministic algorithm A2 to find the solution for T2. Okay, now we are going to utilize this algorithm to obtain a solution for the problem T1. Let I be an arbitrary instance of the problem T1 for which we need to have an algorithm. Now note that there exists a polynomial time deterministic algorithm A2 for deciding the problem T2. So given an input, the algorithm will say yes or no, whether the answer is yes or no. Recall that we are only looking at decision type problems. Now I can tell you how we can construct an algorithm A1 for the first problem T1 by utilizing the algorithm A2. What I do is take an arbitrary input I to the problem T1, compute f of I, and then feed that f of I as an input to A2. Then by the definition of reduction, we know that f of I is yes if and only if I is yes. Answer for the problem T1. That is reduction. Reduction means if you are getting yes as the answer for the problem T2 on f of I, then S must be the answer for I in the problem T1. Similarly, the no case. So if you remember what we did in the previous lecture, this is easy to understand. So now we are getting a polynomial time deterministic algorithm for T1, and hence we are proving that T1 is in the class P. Okay, from this claim you can have a corollary. What is it saying? If you know that a problem B is in class P, and if we can show that another problem A can be reduced to B in polynomial time, then you can conclude that the problem A is also in class P. This is an application. If you already know that B is a problem in class P and there is a polynomial time reduction from A to B, then you can conclude that A is also in class P. Another application, now we have seen an application where you can use reduction to prove that the problem is in class P. Now we are going to see another application where you can use polynomial time reduction to prove that a problem is in class NP. A very similar case, suppose T1 is polynomial time reducible to T2, and now you have T1 not to be in class NP. Okay, previously we had T2 in class P, then we can conclude that T1 is in class P. Now we are having a situation where T1 is polynomial time reducible to T2 and T1 is not to be in class NP. You can then prove that T2 is also in class NP. That means if you can reduce a class NP problem using a polynomial time reduction function into any other problem, then the other problem must also be NP. Proof by applying the method of contradiction. Assume for the purpose of contradiction that T1 is in NP and T2 is in the class P. T2 is in the class P means there exists a polynomial time algorithm A2 to solve T2. Then use the same construction that we used for the previous claim. Now we have an algorithm A2 for T2. From that we are constructing an algorithm A1 for T1. It is the same construction. And thus we are getting a polynomial time algorithm A1 to compute T1, and hence T1 must be in class P by definition of class P, because there exists a polynomial type algorithm A1 to solve T1. And in this lecture we are already discussing about deterministic algorithms. And this is a contradiction because we already know that T1 is in class NP, means no deterministic polynomial time algorithm exists. Thus we have seen two applications for polynomial time reduction. The first one is to prove that certain problems are in class P, and the second application is to prove that a problem is in class NP. It depends on whether you know the RHS problem is in class P or the LHS problem is in class NP. And here the corollary is that if you can reduce a problem A in polynomial time to a problem B, and if you know that A is in NP, then B must be in NP. Now we have enough information to define the class NP complete. I am giving you the definition directly. A problem A is said to be in the class NP complete if A is in the class NP. Okay, it is an NP class problem. Also, if you look at any other problem in the class NP, you can reduce that problem in polynomial time to A. That means any other NP problems can be reduced in polynomial time into an NP complete problem. So this is the definition. What is NP completeness? A problem is said to be NP complete if it is an NP problem and also it satisfies the condition that any other problem in the class NP can be reduced to this NP complete problem in polynomial time. Any such problem is an NP complete problem. Now from the definition we can have a theorem. If there exists a polynomial time algorithm for any problem in the class NP complete, then all problems in the class NP can be solved in polynomial time. That is, then P is equal to NP. The class P and NP are same. This is an unknown problem whether P is equal to NP or not. The solution is unknown. And that is the nice property of this NP complete problems. That is, if you can find a deterministic polynomial time algorithm for any of the non-NP complete problems, then P is equal to NP. We can prove it, prove the theorem. Suppose A is an NP complete problem and there exists a polynomial time algorithm for A. And let B be an arbitrary problem in NP. Now, if A is an NP complete problem, then from this definition we know that an arbitrary NP problem can be reduced to A in polynomial time. Okay? Now, if there exists a polynomial time algorithm for A, then from corollary A, we know that there exists a polynomial time algorithm for B as well. So what is B? B is an arbitrary problem in the class NP. So we are proving that if an NP complete problem A is having a deterministic polynomial time algorithm, then every class NP problem is going to get a polynomial time deterministic algorithm. and hence P is equal to NP. So these are NP complete problems. Now we can see yet another application of polynomial time reduction here to prove that a problem is NP complete. We have seen an application where it is used to prove that a problem is in P, another application to prove that a problem is in NP, now the third application to prove that a problem is in NP complete. Suppose the click problem, you know the click problem, right? Given a graph and a natural number k, say whether the graph is containing a click of size k or not. Now, if you know that click is an NP complete problem, then you can prove that the vertex cover is an NP complete problem, because in the previous lecture we have seen a polynomial time reduction from the click problem to the vertex cover problem. We already know that according to this, we already know that click problem is in NP complete. That means an arbitrary problem in the class NP, say P, can be reduced to click in polynomial time. And here now you have another polynomial time reduction, say another function f2 to reduce click to vertex cover. So you have f1 to reduce an arbitrary NP problem to click, and f2 to reduce the click problem to the vertex cover. Now we can easily prove that the composition of f1 and f2 will reduce an arbitrary NP problem into the vertex cover problem in polynomial time, and you can conclude that the vertex cover problem is in NP complete, is in the class NP complete. And thus now we are using polynomial time reduction to prove that the problem is in the class NP complete. Now here I am copying a figure from the textbook where an arrow shows a polynomial time reduction. These are all non-NP complete problems. Circuit satisfiability problem can be reduced to the satisfiability problem in polynomial time, and which can again be reduced to the 3n of satisfiability of formula in 3n of conjunctive normal form, where each clause is having 3 terms. Then 3NF can be reduced to subset sum. There is a reduction, non-reduction from 3NF satisfiability to click, click to vertex cover to Hamiltonian cycle, and Hamiltonian cycle to traveling salesman problem. And here the reduction is transitive. That means if circuit satisfiability is reduced to satisfiability and satisfiability is reduced to 3 CNF satisfiability, then the circuit satisfiability problem is reduced to 3NF satisfiability. So these are all non-NP complete problems. So if you can find a deterministic algorithm for any of these problems, then you can conclude that P is equal to NP. Another application is, suppose you are given with a new problem for which you are asked to write a polynomial time algorithm, and you are trying your level best maybe for 6 months, but you are not able to get an algorithm in polynomial time. Then it is worth to spend some time to see whether you can reduce your problem into one of these problems. If you can do that, you can conclude that it is an NP complete problem, and it is nearly impossible to get an algorithm for an NP complete problem, because then P will be equal to NP. And that is why one should know about polynomial time reduction and non-problems in the class NP complete. Now we are coming to another class of problems which is called NP hard, more harder than NP complete. A problem A is said to be in NP hard if every NP problem can be reduced to A in polynomial time, right? Very similar to the definition of NP complete class, but here the problem A need not be in the class NP, it can be harder than that. There may not be even a polynomial time verification algorithm for A. So A is more harder, and that is why it is called NP hard. So what is the definition? A is called NP hard if any class NP problem can be reduced to A. Okay, and if A is also in the class NP, it is called NP complete. Now we also need to define one more complexity class, which is co-NP, and to define co-NP we need to discuss about the complement of a problem, and for which we need to discuss about the basis of formal language theory. Let sigma be a finite set of alphabets. Example, sigma be the binary alphabet. Concatenation, denoted by the period operator, is a binary operation on the elements of sigma. Example, if you concatenate 0 and 1, you are getting 0, 1. Now a string is formed from the alphabets using concatenation. Example, epsilon is a string of 0 symbols. This is a special string with theoretical interest, and these are all strings. 0 is a string. This is the concatenation of 1, 0 and 1. So by concatenation you can form all binary strings. And given an alphabet set sigma, sigma star denotes the set of all strings over sigma. For example, if sigma is the binary alphabet set, then sigma star is the set of all binary strings. Strings of length 0, unique, epsilon. Strings of length 1, strings of length 2, likewise equals. Set of all binary strings is sigma star. Now, in formal language theory, a language over an alphabet set sigma is any subset of sigma star. So that means it is basically a set of strings. Examples. Null set is a language because it is a subset of sigma star. Now, given sigma star as the set of all binary strings, consider this language. The set of all binary strings with 0, 1, 0 as a substring in that string. A string is in the language if it contains 0, 1, 0 as a substring. Now let us look at another language L3. What is it? The set of all binary strings X said that 0, 1, 0 is not a substring in X. Okay? Now you can see that there is a relationship between L2 and L3. What is it? L3 is the complement of L2. If a string is not containing 0, 1, 0 as a substring, it is in the language L3. Otherwise, it is in the language L2. So it's a mutually exclusive set and actually complement. So you are getting what is a complement of a language, right? It's actually sigma star minus that language. Sigma star minus L2 is this language. Now before we define the class co-NP, let us see how we can have a binary encoding for an object. Now for an object we are considering a graph. Here you are given with a graph with 4 vertices and 3 edges. Now we can have a binary encoding for the above graph where the vertices can be encoded as 0, 0, 0, 1, 1, 0 and 1, 1. These are the binary encoding for vertices. V0 is represented as 0, 0 or it is represented as the binary string representing the subscript. Okay. Now what is an edge? Edge is a pair of vertices. So this edge is represented as 0, 0, comma 0, 1. Okay, there is an edge between these two vertices. Similarly, you can represent other edges as well. Okay, if G is that graph, in angular bracket G means binary encoding of the graph. And similarly, any object can have a unique binary representation, which all of you know because In digital computer, whatever you store in the computer is stored as a binary string. So that's a non-fact. Now you can see how can you view a problem as a formal language. Maybe a strange concept, but an example will tell you how can you treat a problem as a language. Question: can we represent a problem as a formal language? The answer is yes, we can represent. Example, you consider the shortest path problem. So what is it? Given a graph and two vertices in the graph u and v and a natural number k, the problem is to check whether there exists a shortest path from u to v with the length k. That is the problem. Now I am giving you a language representation of the problem shortest path, which is represented as a language SP, shortest path problem. And this is the language. The set of all strings of this form, 4 binary strings, is an element of a language. It is a quadruple, a binary encoding of a graph, the binary encoding of the vertex u, binary encoding of the vertex v, and the binary encoding of the vertex k. So a quadruple of binary strings is in the language if the graph represented by this binary encoding contains a length k path from the vertex u to the vertex v. Okay, that is the language. Now, an algorithm for this language is assumed to accept a string of this form if and only if there exists a path in G from the vertex u to the vertex v with length k. Length means the number of edges. Okay, I hope you are getting what I am telling. So you can view a problem as a formal language that you can do for any problem. But some experience is required to phrase it as a formal language. So please take it as granted. A problem can be represented as a formal language. Now, once you represent a problem as a formal language, you can talk about the complement of that problem or the complement of the shortest path problem. Here is what the set of all quadruples of binary strings such that there does not exist a path from u to v with the length k. That is the complement. Okay, and the only take for or the thing that you have to remember from here is that there exists a complement for a problem. That is the only thing that you need. Okay. Now with that, we can try to define the class co-NP. This is the definition. A problem A is said to be in the class co-NP if the complement of that problem is in the class NP. That is it. When a problem A is in co-NP, when its complement, the complement of the problem is in NP. So that is the definition. Now we are coming to the last part of this lecture, where we are going to recollect the complexity classes that we discussed in the last 3 lectures. We know that the problem of checking whether P is equal to NP is an unsolved problem for the last 51 years. And we discussed about the classes, complexity classes, P, NP, NP complete and NP hard, and also co-NP. But now I am going to show you a Venn diagram which includes all these classes except co-NP. And the Venn diagram is an assumption by the theoretical computer scientist. I hope you know about the Venn diagram. This is the class NP problem, the set of all problems. And they believe that the class NP is a strict superset of P because They don't know whether P is equal to NP or not, but they believe that they are not equal. NP is more harder than P. And from the definition of NP complete, we know that an NP complete problem is an NP problem satisfying a very nice property that any other NP problem can be reduced to it in polynomial time. And what is NP hard? NP hard problem can be outside the class NP. It may not be always NP. What is the definition? A problem A is said to be in NP hard if an arbitrary class NP problem can be reduced to the problem A in polynomial time. And this is the assumption about the relationship between various classes. But if someone comes with a polynomial time deterministic algorithm for any of the non-NP complete problem, then all this collapse to a single set. But no one knows whether it is possible or not. But it's very unlikely is what theoretical computer scientists believe. Today we define the complexity classes NP complete, NP hard, and co-NP. And the class NP complete is having a nice property that if we can find a deterministic polynomial time algorithm for any of the NP complete problem, then we can conclude that the class P is equal to class NP, which is an unsolved problem for the last 51 years. Thank you.